So we are going to practice a little bit more with electron configurations today, and we're gonna connect the configurations to the quantum numbers and basically kind of give you some examples of the problems that you're gonna see on the test, and then what to expect, basically. So we have labeled the periodic table last class, and here it is again labeled again, and we are going to write a couple of configurations. And last class we introduced the longhand configuration basically and the noble gas notation. So let's write the configuration for I would say selenium, which is number 34 right here. And we're gonna write it the long way and then the shortcut. Okay, just to kind of refresh your memory. So selenium number 34. Atomic number 34. So anytime you write a configuration, you have the periodic table in front of you that's labeled, you basically start reading it from left to right with, starting with the first period. So the first thing is move this helium over here because it's an S block element. So I have 1s2, and then comes 2s2, which would be these elements. So basically to get to selenium, which is here, I have to go through all the elements that are in the periodic table. Meaning the electrons that selenium has the 34 electrons, occupies the orbitals based on Aufbau principle, the closest to the nucleus, in the lowest energy level orbitals, and then they go outward based on the energy. So that means first electrons in the 1s orbital, the second 2 electrons in the 2s, and then comes the 2p. All 6 electrons are occupied in the 2p, that's why we call this 2p6, and then 3s2 and 3p6, and then that 3p6 puts us at argon, and then we have 4s2, and then we have 3d10, and then we are going to have 4p4, right? 4p, and selenium is 1, 2, 3, 4, the fourth time, the fourth one in the 4p orbital. Good? So this is the longer version. The shortcut to the configuration is the noble gas notation, meaning you have to find the noble gas before selenium, before. Every element is located between two noble gases, the one after, which would be kryptonium, and the one before him, which is argon. So to determine which noble gas you use, you put your hand on your element and you go one level up, and then towards the end of where group number 8 is. So in this case, we're talking about argon. So instead of writing the whole thing, selenium can be written as argon, and we put the argon in the brackets, okay? And then we're gonna add what is missing from the from this. What's missing is your 4s2, 3d10, 4p6, right? So for the elements that are in the s and the p orbitals, the valence electrons are always located. The valence electrons are the electrons in the outermost level, right? So the valence electrons are always located in the s or the p orbital. This element, selenium, the highest energy level for selenium is the fourth level, 4s and 4p, correct? Okay. 3d is complete. 3d10 is complete. So 3d10, so this, if you look at the longhand configuration, these are your valence electrons. Because you have energy level number 1, energy level number 2, energy level number 3 is made of the 3 sublevels, 3s2, 3p6, 3d10, and some of you that want to put them all together, that's fine too. I just write them the way they come up in the periodic table, okay? But if you want to say, write this configuration in an organized manner, you can put 3s2, 3p6, 3d10, and then end up with the 4s2 and 4p6. The fourth energy level is the highest energy level for selenium.
I think it's 4p4.
4p4, I'm sorry. Yes, you're right. Thank you for correcting me, for catching it. Okay, so basically, my valence electrons are the highest level electrons in the highest energy level. So for this element, which is a p block element, the valence electrons are the electrons in the fourth energy level, right? Everything before that are called core electrons. They are the electrons that are underneath the valence level. So in this case, I have 4s2 and the 4p4. Those are the valence electrons. So valence electrons in the 4s2 and the plus the 4p4. So 2 electrons plus 4 electrons is 6 electrons are valence electrons. Okay, 6 electrons are valence electrons. For the representative elements, what gives you the valence electrons? The number of the group, right? Remember from way before. The number of the group tells you how many valence electrons you have. In this case, selenium is in group number 6, it's 6 valence electrons, but now we can actually see what those valence electrons are. In 2 of them in the 4s orbital, and the 4 of them in the 4p orbital. Okay, now, you're going to get questions like this. Write the quantum numbers for the valence electrons in an element, okay? So once you establish what the valence electrons are, you look at the highest number here for the energy level, and the highest number is, sorry guys about this. The highest number is number 4, and in all this configuration, 4 is the highest number for the energy level. That's where the valence electrons are located. So once you determine where the valence electrons are, you can write the quantum numbers for these valence electrons. So a 4s orbital, if you remember how we draw it, contains these 2 electrons, right? That's the 4s. So if we are to write the quantum numbers for these valence electrons, I can put n equals 4 for the principal quantum numbers, L equals 0 for the s orbital, right? The magnetic number for the s orbital is always 0, and the spin, in this case, I have 2 electrons, so it's going to be plus and minus 1 over 2. So these are 2 sets of number for these 2 electrons, the 4s electrons. Now, that's not finished. We have to write 4 more sets for the p electrons. For the p block, the 4p orbitals, if you remember any p orbital, we write it in a set of 3 lines, right? So this is your 4p orbital. And in the 4p orbital, you're gonna put 4 electrons. According to Hund's rule, you're gonna put 1 by 1 with the spin up, positive 1 over 2. And then you're gonna come with the 4th one with the spin down, correct? Okay. So if you look at this, n equals 4, the principal quantum number, L equals 1 for the p orbital. The m, now to determine the m, you actually have to do the drawing, the diagram, because you have to figure out what box is occupied. And in this case, all the boxes are occupied. We have all 3 versions of m, my negative 1, 0, and 1. This would be your negative 1 box, this would be 0, and this would be 1. Okay, and then in terms of the spin, I have electrons with a spin plus 1 over 2, all these pointing upwards, and I have this little dude here that's pointing downwards. So I can say I have both plus and minus 1 over 2. And by writing it like this, you actually have given me 4 sets, a set of 4 numbers for each single electron that you have. Good? Now, so that's the valence electron story. Now, another question that you can see on the test is, what are the quantum numbers for the last added electron? The last added electron. And in this, the last added electron is always the electron in the orbital or sublevel that corresponds to the block where your element is. So if you have a p block element, the last added electron is one of these at the end, but it's located in the p orbital because your element, selenium, is a p block element. So the last electron that comes to occupy the 34th electron of selenium will go into the p orbital. Okay, so basically your last added electron is an electron in the 4p, so it's one of these, but which one? Which electron is the one that you draw the last? So you draw 3, and the 4th one is this, right? So the quantum number for the last added electron is n equals 4, because he's in the 4p orbital, L equals 1. And then now you know what box he is in. He's in the first, the negative 1 so-called box line, okay? And then the spin for this guy is negative 1/2. So if I'm gonna ask you for the last added electron, always look at what's coming at the valence electron. It's one of the valence electrons, it's always one of them. But it's the one, if you have more sublevels occupied by valence electrons, in this case valence electrons are in the 4s and 4p, which one would you choose as the last added electron? The one that is in the sublevel that corresponds with the block where your element belongs. This is a p block, you have a p, the last added electron in the p orbital. Another kind of question that you can have is, how many unpaired electrons do you have? To figure out the unpaired electrons, you basically have to draw out the valence electrons, because the unpaired electrons can show up because of Hund's rule. So if you look at selenium, the valence electrons are 4s2, 4p4. If you divide this by 2, you're gonna have a pair here and 2 pairs here, but it doesn't work like that because of Hund's rule. So this 4s2 is completely occupied, they're paired up, the 2 electrons in an orbital. And then here you have these 2 here are paired up, but you have these 2 here that are not paired up. They don't have the second electron placed in. So just because there are 2 electrons, in this case, that 2 electrons do not make a pair because they are in different orbitals, they're placed in different lines according to Hund's rule. So in this case, for selenium, it has 2 unpaired electrons. Go with that? Okay, now, let's do another example. Let's talk about, let's do the same story, the same questions, but for an element that is in the D block. I'm gonna say cobalt. Okay, let's do it for cobalt. So if I wanna write the configuration of cobalt, and I'm gonna write the shorthanded version. The configuration of cobalt starts with number 27. You go up 1 line and to the end. So argon is your noble gas. So cobalt is like argon, to which you have to add what's left. 4s2 and 3d, 1, 2, 3, 4, 5, 6, 7. 3d7. So 4s2 and 3d7. Okay, so in the previous case of selenium, the valence electrons were in the 4s and the 4p orbitals. Okay, so for the s and the p block, the valence electrons are always in the s or s and p orbitals. But in this case, this is an element that belongs to the D block. And everything that you write after the noble gas, basically all of these are valence electrons. Okay. Now you would say, okay, but the 4s has a higher number than the 3d. So this belongs to the 4th energy level, and this belongs to the 3rd energy level, and that is right. But in terms of energy, this is a little bit an exception. 3D level has a higher energy than the 4s. 4s is further away from the nucleus. It should have the highest energy, but because it's a simpler orbital, this 3D that has already 7 electrons in there, the repulsion between the electrons is stronger and it's going to create a higher energy. So for the D block elements, the D orbitals has a higher energy than the 4s, than the s orbitals. Okay, just keep that in mind. So the 4s gets occupied first completely because the outball principle says the electrons are occupy the lowest energy orbitals first. So 4s gets completely occupied, and that's why you have the d orbitals being in the course of being occupied little by little by these elements, because they have the higher energy. Okay, for the d orbitals, for the d block elements. So the valence electrons are these, both of them, but the last electron, the last added electron, was going to be in the d orbital. Okay, so if I'm going to say this, write the quantum number for the last added electron. in this element, in cobalt. Okay, because you look at what comes after the noble gas, which are valence electrons, so the cobalt has 2 plus 7, 9 valence electrons, okay? But the last one, the last electron is going to come in the d orbital. So I'm having the 3d and is the 7th electron in the d orbital. So how am I gonna write this? So the n equals 3, L equals 2, that's for the 3d. Another m, to be able to detect what m I need, I have to draw the lines, I have to do the diagram. So d orbital comes in a set of 5 lines, right? And then I'm gonna have to put the 7 electrons. So I have 1, 2, 3, 4, 5, and then 6, 7. This is your last added electron. Okay? So you have to figure out what's the name of this line. So it starts with a -2, -1, 0, 1, and 2. So M would be this one right here, -1. Okay? And then the spin of this electron, because I put it with an arrow pointing downwards, the spin of this electron is a -1/2. Good? Another question, how many unpaired electrons? To be able to tell the unpaired electrons, you basically have to draw the d orbital. And if you, like we did here, we draw the d orbital, so you have 3 unpaired electrons. Right? 3 unpaired electrons, 3 lines that are not matched up with other electrons. So when you look at the configurations, and you get questions about the last added electron, or you get questions about the valence electron, you write the noble gas. What's coming after the noble gas, if an element is a d or an f block element, those are your valence electrons. If an element is a s or a p block element, the valence electrons are given by the s and the p orbitals only. Because for selenium, we had to put the 3d orbitals when we wrote the configuration, but those 3d orbitals were not valence, were core electrons. They were underneath, in a level that it was lower than the 4s and the 4p. Good? That's another thing that I wanted to address. When you are going to look at elements in a group, so let's look at a little bit of at the configuration. I'm looking at the elements in group number 1. What do I see as their valence electron? So the noble gas is something here, and then you add. For lithium, you add 2s1. For sodium, you add 3s1. Potassium is 4s1, 5s1. So all the valence electrons for elements in a group have the same configuration. They are in the same orbitals. Depending, the only thing that's different is basically the principal quantum number, but everything else will be the same. If you take group number 7, all fluorine is gonna have 2s2, 2p5 after the noble gas. Chlorine is gonna have 3s2, 3p5. Bromine is gonna have 4s2, 4p5, 7 valence electrons. So they all have the same configuration basically. So the valence electrons for all the elements that are in a group have the same electronic configuration. That's why they are elements in a group that I consider a family, because they behave in the same chemical and physical way that is dictated by the valence electrons. They're having the same valence electrons in the same orbitals. That makes them very, very close in terms of behavior. That's why they're called families. Okay? So that's another thing that I wanted to tell you. Whatever it is included in the noble gas, when you write the noble gas configuration, you put whatever in the brackets. Those electrons in the brackets, those are considered to be the core electrons. And after the core electrons come the valence electrons. The core are in the level that are underneath, and the valence electrons are in the outermost level, always. Okay? What else do I need to tell you? When you have, let's talk a little bit about ions here, because now the concept of ions that we discussed about in chapter 2 start to kind of fall into place. If I want to write the configuration of chlorine, so chlorine is like neon in the brackets, noble gas neon, and then I add, for chlorine, I add 3s2, 3p5, right? So he has 5 valence electrons. The last added electron is this 3p, the 5th electron in here. Okay. Now, chlorine wants to be like a noble gas, like he wants to be like argon, right? So what happens is this 3s2, this is completely filled with electrons, and 3p5, 3p has 5 electrons. A p orbital is completely filled with electrons when he is at 6 electrons. Orbitals that are completely filled with electrons are the most stable. Okay, that's why the noble gases that have this p6, s2p6, all of them have that configuration. That's why they are so stable. They're noble gases, because the s and the p orbitals in all these noble gases are completely filled with electrons. That's perfection. That's where the octet is. So for chlorine to have the octet complete, it's going to add another electron right here to make this a 3p6. So chlorine adds 1 electron, basically, and from a 3p5, but adds it here and fills out the p orbital. And that creates the octet. S2 with a p6 is an octet. So chloride, the ion chloride, has the configuration neon 3s2 and now 3p6, which is nothing else but argon, right? So you can write it like this, or you can say chlorine with a -1 is argon in the brackets. It's exactly the noble gas. Now let's see what happens with calcium. Calcium is right here. Configuration is right here. What's the noble gas for calcium? If you look it up, it's going to be argon, right? So calcium is argon followed by 4s2, correct? So calcium has the configuration of argon, which is 3s2, 3p6 at the end, has the octet, and he has these 2 extra electrons. He's going to get rid of them, and he's going to become just like argon, because the octet is there for argon. He has the 3s2, 3p6 already. So by explaining it like this, it makes more sense, because you're gonna see actually the octet being formed. You're gonna see that argon has a 3s2, 3p6, the 8 electrons, that's gonna make him like being super stable. Okay, so noble gases, the reason for them being so stable and not reacting and not being inert, basically, is because they have the orbitals s and p completely filled with electrons. And an orbital s, if it has 2 electrons, is completely filled. An orbital p with 6 electrons is completely filled. A d with 10 and an f with 14. Those are completely filled orbitals. When you get this situation, you have elements that are extremely stable, just the way they are, and they don't need to lose or gain electrons to do that. Okay? Now let's see what happens if I have these guys in the middle. These transition elements in the middle, they're metals, so they're gonna lose electrons, make cations. Remember, we talked about that in chapter 2. So let's look at how is this going to happen. If I wanna see iron. Let me erase this. If I'm looking at iron, you know that iron, just by remembering what the periodic table with charges was saying, is that iron has Fe, has argon in the brackets, and then we have 4s2 and 3d, 1, 2, 3, 4, 5, 6, right? So argon, 4s2, 3d6. Good? Now, anytime you have a d block element, the first electrons that are going to be lost, they're going to be given away, are from the 4s orbital, because the 4s orbital, even though it doesn't have the highest energy, because remember when I told you that 3d is a little bit higher than 4s, very, very close, but just a tiny, tiny bit higher. The electrons are lost from the orbital that is further from the nucleus, the furthest orbital. 4s is in the 4th energy level, 3d is still in the 3rd energy level. So they're gonna lose this 4s electron. So iron, if he wants to become Fe2 plus, he's gonna lose these 2 electrons. It's like argon, and he loses this, all he has left is a 3d6. Good? That is the configuration of Fe2 plus. The s2 orbital electrons go first. Okay. But we also have Fe with a plus 3. The Fe with a plus 3 loses the s2 electrons and an electron from the d6. So it's going to be argon, that he lost the s2, and we're going to have a 3d5. So he loses these 2 and 1 from here. So 3d5 would be the configuration of an Fe with a plus 3. So that what I need to point out, what I want to point out to you is that, this has to go away. Oh my God. That when the multiple charge ions happen, they happen because these elements have the ability of losing electrons from the s orbital and also from the d orbital. That's the reason why. Now you can understand that part as well. Versus these metals here can only lose electrons from the s orbitals only. They don't have, and they lose the electrons that they have and nothing else. Okay, so that is the ions. And there's one more little topic that we need to address, and that is the exceptional configurations. Remember when I told you that the completely filled electron orbitals are the most stable? That goes for the d orbitals as well. The next more stable are the halfway filled orbitals. And anything after that is whatever it might be. So if I have the configuration of zinc, and then I'm going to compare with the configuration of copper. If I look at zinc, zinc is argon followed by 4s2, 3d10, right? So this is argon, 4s2, 3d10. Completely filled orbital, super stable, okay? Copper, on the other hand, this little guy here has 4 argon, 4s2, 3d9, right? 4s2, 3d9. Now, because s orbital, the 4s and the 3d are just a little bit of difference in energy, but not a lot. And a d10 orbital is more stable than a d9 orbital. They're going to play a little trick. So they're going to say, okay, I'm going to steal 1 electron from the s orbital and move it into the d orbital. So instead of having a 4s2 3d9, copper has to be spelled out, written as a 4s1 3d10. Okay, 4s1 3d10. So basically, instead of having a completely filled s orbital and a random d9, copper makes it when he has a halfway filled orbital, which is pretty stable, and a completely filled d orbital. Okay, everybody that is like copper with a d9, copper, silver, gold, whatever, all of these elements, anytime you write a configuration and you see a d9, switch it. You're not going to have a d9, you're going to have a d10 by moving an electron from the s orbital. So that is an exception to the Aufbau principle, basically, because here it's a violation of Aufbau principle. This electron in the s that has lower energy will make a jump and occupy a d orbital. Okay, so there is no such thing. If you see an s2 d9 that doesn't exist, it's going to become an s1 d10. Okay, and when I'm asking you for unpaired electrons, the d10 are all paired up, and you have the 4s1, 1 electron unpaired in the s orbital here. Okay, but the last added electron is still in the d orbital, the 10th one in here. If you think about it, because it's a d orbit, it's a d block element. So that's the situation with this. So any element that is below copper in the d9, silver will not have an s2 d9, will have an 5s1 4d10, and so on. Okay, so that's the situation with, and you have to be careful to look at the s orbital, do not confuse it, because I say, how do you identify, I'm giving you a configuration like this, and I want you to identify the element. I'm gonna say this is, argon, don't forget to put argon here. Before. Argon 4s1 3d10, and you're gonna say, oh, who's the 3d10? I'm gonna look and I'm gonna say zinc. Pay attention, it's not zinc, because s2 is not complete, it's an s1. So I can give you a configuration and ask you to identify the element. The moment you want to do that, if I say, what is this? And I don't tell you it's zinc. You look 3d10, okay, remember, make sure that it's not an exceptional configuration. And that only happens for these elements, and I'm gonna show you 3 more that do the same thing, okay? So, only for the D block. So here, because you have S2 and D10, or you can do the math on the electrons. Argon has 18 plus 2 plus 10, 18 plus 18 is 36, who's 36? Or whatever that is, 30, what is it, 18 plus 2, yeah, 30. 30 is zinc. So you can do the math on the electrons if you're not sure how to handle this. Okay? Now, another situation when we have exceptional configurations are these elements that are in the D5, 1, 2, 3, 4, 5. These manganese, technetium, rhenium, and all these. So if you look at manganese, you write it as argon followed by 4s, argon in the brackets, 4s2, 3d4, right? 1, 2, 3, 4, 5, 3d5, sorry, 3d5. So this is an element that has s orbital completely filled and the d orbital halfway. In every spot in the d orbital there's 1 electron. What about krypton? Chromium. It's argon, 4s2, 3d4, and here it is. 3d4 is so close to a 3d5 that this situation with switching an electron from the s in the d orbital will start again. So instead of writing it like this, you have to write it as argon 4s1 3d5, because a d5 orbital is halfway filled, an s1 orbital is halfway filled, and that creates more stability. So in other words, there is no s2 d4 because it becomes s1 d5. Just remember these in terms of exceptional configuration. So what elements are going to have these little tricks done to them? The elements that are a D9, these 3 here, and a D4, which are these 3 here, these 4 here. Okay, these are the D4 elements are D5s, the D5s are the real D5s, and the D9 are the D10, and the D10 are the real D10s. Okay, so you have to keep that in mind. We go with this? Okay.